Hello, everyone. Welcome to the webinar. We'll get started in just a moment here. Right. Thank you to those of you joining us for today's webinar. This is the second webinar in the series we're doing on the 7.4 magnitude earthquake that struck Taiwan in April of this year. I think some of you hopefully were able to attend the first webinar 2 weeks ago. If not, we'll be sharing the recording and the slides from those presentations on the page for this earthquake on the Learning from Earthquakes website. So I'll put that in the link. I'll put that link in the chat later on. But welcome, my name is Elizabeth Angel. I'm EERI's Communications and Program Manager. And for those of you who might not be familiar with EERI, I just want to take a brief moment to talk about our organization. The Earthquake Engineering Research Institute is the leading nonprofit membership group bringing together professionals from a wide range of backgrounds and disciplines, both in the US and around the world, who share the common goal of working to better understand earthquake risk and advance earthquake resilience. So we have members ranging from students to retired folks from a wide range of fields and disciplines, both academics and practitioners. And if you're interested in joining us and becoming part of this community, there's the link there. I can share that in the chat as well. We'd love to have you. Our flagship program is the Learning from Earthquakes program. And so on that note, I'm going to turn it over to today's moderator, Professor Eduardo Miranda, who's the co-chair of Learning from Earthquakes.
Thank you, Elizabeth. Welcome, everyone, to this second webinar on the series on this important earthquake that occurred earlier this year. I co-chair the LFE program with Mike Miller, and as Elizabeth mentioned, we like to think this is one of the most important programs within EERI. One of the things that we do is learning, and we're always trying to improve the program. So we have prepared this survey, and it's a very short survey, and that you will get toward the end of the webinar. And we would appreciate very much if you can fill that out just before you log out. The other thing is that this webinar series is made possible from the endowment that we have. We've been raising funds to fund some of these activities. And this webinar series is an example of the activities that we fund. So if you're able to fund, we invite you to do so. And that in our website, you see the link that it's copied over here. And the other thing, another one of the programs that we have in EERI, it's called the Housner Fellows program, that it's made possible thanks for a very generous donation by Professor George Housner, who was a very famous professor at Caltech. And you will hear from Maria Mohammed today, and the kind of things that we're able to do with this. And this is complemented from additional funding from the Federal Emergency Management Agency, FEMA. So with that, I will go ahead and introduce our speakers. The first one is Dr. Wei-sen Li, who's the Director General of the National Science and Technology Center for Disaster Reduction in Taiwan. And in particular, what we will be hearing about is, it's of course seismic activity and this earthquake that we had in Philippines. Philippines, just very briefly, it's located at the intersection or junction of three very large plates: the Philippine plate, the Euro-Asian plate, and then the Sunda plate. And in particular, a lot of their seismicity is controlled by two subduction systems, one in the Ryukyu Trench and the other one, the Manila Trench. And in particular, a lot of the activity that occurred in this earthquake was centered around the city of Julian, which is located near the intersection of the coastal range, which is a system of faults that are running on sort of north-south direction on eastern part of the island. And then this intersects with one of these trenches, this Ryukyu Trench, And because of this intersection, it's really, really active. There was a very large earthquake in 2018 in February 16 with a magnitude of 6.4, produced very large earthquakes. And now we get this other one, but much stronger, 7.4. And so with that, I pass it on to Dr. Li.
Thank you, Co-Chair. Good morning and good afternoon to everyone. I'm Wei-sen Li, as the previous introduction. On the eve of Chichi earthquake, 25 years afterwards. So today I'm glad to have a chance to share about 25-year preparedness for the big one. Today I want to emphasize how we learn from Chichi earthquake by using science and technology to reshape disaster risk management in Taiwan. So I just make a simple comparison between the Hualien earthquake happened this April and the Chichi earthquake hit us in 1999. Besides its magnitude, besides its casualty, today I want to focus first item about emergency response. 25 years ago, when Chichi earthquake hit, actually, I would like to say it could be our dark age about emergency response to earthquake. At that time, besides we learned experience from Northridge earthquake and Kirby earthquake, we had little idea about how to deal with the urban type earthquake. But from the Chichi earthquake, we know we must do something to lower impact by next big earthquake. So I will share how my office use science and technology to better enhance, to better help emergency response at the first few hours of the earthquake. That is something impossible in the 1999. Another thing I want to emphasize about the interruption to critical infrastructure, especially highway and railway. In 1999, we suffered a huge losses about critical infrastructure, especially about the power grid. But for this time, we didn't suffer any interruption about power grid. Even our railroad, the highway along East Coast just have the very temporary interruption, less than 24 hours. But later on my slide, I will tell cascading impact. In Taiwan, we not just have earthquake, we also have typhoon. So this is a never-ending story. What we learned in the last 25 years, especially how we prepare for the big one, like Hualien earthquake, I think we see in the 25 years, we learn a lot. First of all, I think from the previous webinar, we talked a lot about the structure destruction. Most important thing since earthquake is we change the building codes. We emphasize lateral reinforced bar. We emphasize spacing of reinforced bar and also emphasize concrete strength. And also look at how we increase infrastructure resilience, especially about power grid. In 1999, we just had one loop, but now we have 4 or 3 loops to ensure even in case one loop have problem, we still can have infrastructure resilience. Another one is early warning system and public awareness. In 1999, we might spend 1 minute to identify location of hypercenter, magnitude, and intensity. But till the 2024, now the CWA, Central Weather Administration, needs 7 seconds to identify those parameters. And we can disseminate those information through the public warning system. So everyone can receive information. Today, we will have the national drill on earthquake. On 9:21 a.m. in the morning, everyone in Taiwan, including tourists, will receive a message, alarm, we call national level alarm on your cell phone. So everyone encouraged follow shakeout procedure, drop, cover, and hold on. Another about public awareness, you see, this is real picture of our kids when they met earthquake in April. Because they have drilled for many times, their teacher told this time, those kids respond quickly and more efficiently than drill. So it's good we had public awareness. Another one about disaster response management, I will tell later, how we integrate everyone together. Like my office, NCDR, is located in our National Emergency Operations Center. On April, when the earthquake hit, morning, working time, so immediately my office go downstairs to join emergency response immediately. Another one is community and international support. I mentioned in the past, we learned a lot from EERI and California Emergency Office, and also from Japan. We learned your experience and combine our characteristic. So we have our own way to reduce earthquake. Another one is continual improvement and learning. So we enhance learning in school. By the way, about infrastructure resilience, you see, this is two abutments connecting the East Coastal Highway, but luckily we had a redundant highway here. So this is why after the huge interruption to the highway, we can still resume its operation within 24 hours. Last part about public-private partnership. Since the Chichi earthquake, we learned one thing. The private sector, especially NGO, have more power and mobility than government. So this is real picture after Hualien earthquake. NGO operate one shelter immediately. This is my experience in the last 20 years. Whenever I join my office as the disaster management. From the global trend, it starts from the Hugo framework for action. Till now, we are under the Sendai framework for disaster risk reduction. I think in the last 20 years, Taiwan have the three different phases change, especially about disaster risk management, especially at the emergency operation part. First of all, I call it experience based. We rely on leadership by the emergency responder. At that time, they don't think a group of scientists can give them good advice about how to respond. So that time I will describe low mutual trust, try and error by actions, we're learning by mistake, little information exchange. Later, because with the HFA, with more interaction with emergency responder, finally they think science and technology and data can make everything differently. So I will call this period from 2009 to 2014 a science base. So we had a mutual trust. We try and error by science and technology. We embrace open attitude. We share more information than ever. We're learning by sharing. Now, especially starting from the 2014, I call it enter the age of information intelligence base. I'll explain later. How we produce very good information intelligence, no matter for the decision maker, emergency responder, even to the general public. So now is the whole society environment in Taiwan. We emphasize co-design, co-work, co-implementation, consider both about disaster risk reduction and climate change. Very important part to have the good emergency response in Taiwan. Very important thing, how we integrate information from different government agencies. Though NCDR is the research institute supported by National Science and Technology Council, just like NSF in the US, but we have a lot of the partnership among all government agencies. For example, we have the rain gauge from CWA, more than 1.5 thousand, water level, flood sensor, CCTV. So we can all massage and integrate the data, produce kind of information intelligence. This is one typical image. We combine CCTV. We use the mobile phone signal to identify population distribution every 10 minutes. So immediately we can know how many people in this district, how many people here. So it helps us to make a good decision because we know the population flow. So from the 2009 till now, we operate more than close to, I think number right now, close to 90 disasters. So we use our information platform to help central and local government. Another thing, as I mentioned, earthquake early warning system is very important one in Taiwan, especially we send information to the general public. Starting from the 2014 to 2015, we complete initial phase. So this is something my office co-work with our government to complete the system. This I mentioned from 60 seconds to 7 seconds now. This is alert. We disseminate this April about the earthquake. So now we even include English description for international visitor in Taiwan. Another very important thing, to reach out the general public, we also use the line. Line is not popular in the US, I know, but in the Asia, especially Taiwan, Korea, even Thai, we use the line. We offer the free information, cooperate with the line company. We disseminate a lot of information, like even earthquake, we will push the geo profile of the earthquake near the hypercenter intensity map. But most important thing, we continue to push some information for our subscribers. Now we have 1.6 million users subscribe our channel. Even during this April, because the earthquake, in 1 month, we disseminated about 100 million messages to our users. So we feel the empathy about the emergency information to the general public. Another very important part about science and technology. First of all, we have platform to estimate about damage of earthquake. So it can serve two functions. First, if after any major earthquake, within 10 minutes, we can estimate its impact, highlight disaster hotspot. But for the drill, we can also, like this one, we can propose a scenario for our government to do the exercise. Today, we had a national level exercise in Jiayi, a southern city of Taiwan. But in the 2022, Hualien is our target to exercise large-scale earthquake and the mobilization. We even have kind of 3D model to identify vulnerability in the city because we had a data of each building based on taxation data. And most important thing, we think about next big one. So from a serious program, we from the source of earthquake impact assessment, even try to deliver some countermeasures, is serious about collaboration among government agencies. So the following slide is the true story about how we respond to Hualien earthquake this April. This is the slide 2 hours after the earthquake. This is our former president, our former premier, director of NCDR. We gave them a brief report about impact of Hualien on that day, 2 hours after the quake. So first of all, we provide kind of the information. This part is from CWA about the intensity around the Taiwan, but we also produce this slide, show the location of hypercenter and show the tectonic location about how we have the earthquake, the mechanism of earthquake. All the slides you see here, most are generated automatically by our office system. And another view of cross-section from south to north. About this is hypercenter. Nearby is the aftershock or the previous earthquake hit in Hualien district. And most important thing, we also report back about intensity. From the several years ago, we not just use PGA as the criteria, we also use the PGV to look at the impact, look at intensity map. Another one, we want to integrate information to tell about situation. This is the way we do it. I said we integrate a lot of CCTV camera in Taiwan. On the day we open the CCTV camera, this is the live feed from Hualien. Two things for sure. First of all, electricity is no problem. We can still see the traffic light. And telecommunication is good. So this is why we can have the image in real-time mode. So we can identify some devastation in Hualien. Compared to 25 years ago, everything down. Telecommunication down, mobile phone down, electricity down. So this is great improvement from 25 years ago. Another one, from the crowdsourcing, immediately we collect a lot of the report from the internet, make the world map, situation map to commanding office at EOC to understand the impact. Another one, we also try to highlight some landslide in mountainous area, which is our kind of the long-term impact to us from April, maybe to in the following couple of years. And most importantly, even in north of Taiwan, this is a picture in the new Taipei City, very close to the office, close to Taipei City, a kind of the impact to elevated the subway system. And even I showed this is should be the bridge connecting tunnel and highway, but the huge rock destroy the highway. At the beginning, we think it might interrupt the traffic for months, but the previous slide showed Here is another old bridge. The kind of redundancy can reconnect the highway to the tunnel. Another thing, we also show devastation along the highway number 8. Falling rock hit cars and bus. Another one, we highlight the location of the epicenter and the relevant fort in Hualien. In the 2018, the Meilun Fort is another source created a huge earthquake to Hualien, and also highlight the transportation system under high intensity shaking map, and also highlight some critical infrastructure in high shaking intensity. Likewise, even the power system, especially high voltage power tower in the high intensity area. And most importantly, since we know is huge earthquake along in close to the mountainous area in Hualien, so also estimate a possible area have landslide and improve in the following because of typhoon, because torrential rain, we suffer a lot of interruption to highway and railway along the East Coast. And most important thing, we learn one thing, very important, how we provide the quality information intelligence by early warning. In Taiwan, actually, right now we have the multiple early warning system, not just about the earthquake, but also the typhoon. But we think these components are very important to provide the quality information intelligence. And we must understand why we have to provide early warning. Maybe we want to action for protection. We want decision making. We want to respond to developing situation. So this is about the early warning on physical vulnerability. But now we also provide some early warning on the social vulnerability, try to estimate about impact. So very important thing, I summarize why we can advance a lot of topic Taiwan about disaster risk reduction. I think like every country, we had several threats from natural hazard. But in Taiwan, we have serious project funded by NFTC. Of course, we allocate budget, but most important thing, before do any research, we must highlight what improvement we want to have at the project. If we decide scale of budget, item of improvement, then we have a lot of interaction between research community and practitioner, even government want to know what kind of innovation we need, what kind of information we should provide, interaction about how we have the good discussion, how we integrate everyone's idea, and very important thing, we have to implement those science and technology for the practical application. So a very important thing right now in Taiwan about information part related to emergency response. We want to have the disaster risk reduction information supply chain from sensor, from data, from tools, from channel, from information intelligence. We emphasize risk communication. We need facilitated, fill the gap, and we must think about diverse user in our society. So this is right now NCDR work with the research community and our government to provide kind of information supply chain to meet the demand. So a very important thing, I know right now is the age for Internet of Things, but now we still emphasize Internet of Things to intelligent of thinking. So we must emphasize how we apply AI, how we use the better platform to display information, and how to provide solution of action. So that is most important thing. We must action for this different kind of nature hazard. So this is our society. We try to have end-to-end connection. We try to integrate information through kind of the operation unit like my office, and we have to bring the solution to citizen or decision maker. But most important thing, we use over-the-top idea. We use existing network software to push our information to the general public, to the decision maker, to fill the information gap. So this is about, we think data, information, knowledge, wisdom are typical. We create the pyramid of wisdom, but for disaster risk reduction, we need action. So elements are here, scientific prediction, real-time monitoring, in-time decision. So this is the key element we can succeed in Taiwan because a lot of integration. The last slide I want to emphasize, since this April, within 100 days, In total, we have the 2 large-scale events. Beside the earthquake in April, in late July, we have Typhoon Gami. This typhoon is power equivalent to Typhoon Morocco, even more, because this Typhoon Morocco hit Taiwan in 2009, killed about 700 people. But even we have kind of back-to-back cascading impact, that we can still be a very safe country. I think 2 reasons is very important, is preparedness and resilience. So even though we have 2 large-scale events, we can still survive. Thank you very much. This is my sharing about what we learned from 25 years ago till now. Have a good day. Thank you.
Thank you very much, Dr. Li. That was a very interesting presentation, not only the overview of what happened in this earthquake, but in particular contrasting the great number of advances and improvements that have been made over the last 25 years. I want to remind everyone that if you have questions, you may go ahead and type them in the Q&A button that you have on the bottom of your screen, and we will try to answer most of them, or as many as we can, live at the end of the 2 presentations. So I will go ahead and now introduce our second speaker, who is Maria Mohammed, who is a structural engineering at Structural Focus, which is a structural engineering firm in Southern California. Maria is also an EERI Housner Fellow, and she will report on the findings of the Housner Fellows group that traveled to Taiwan in May to conduct not only reconnaissance, but also to test a new functional recovery data collection tool that they had previously developed. And this earthquake provided an opportunity to test it on a real earthquake situation. Go ahead, Maria.
Thank you, Eduardo. Like Eduardo mentioned, I'm Maria Mohammed, and I would like to acknowledge that I'm giving this presentation on behalf of the Housner Fellows class of 2020/22. And this presentation is based on our experience traveling to Taiwan, specifically Hualien, after the earthquake to test a functional recovery data collection tool. Quick presentation outline. I'll give a background on our Housner Fellowship project. This is a project we've been working on for the last 2 years that led to the data collection tool, and our experience testing the tool in Taiwan after the Hualien earthquake. And I will share some of the data we collected from some sample buildings during that test, and these buildings will have, as you can see from my presentation, various levels of functionality. So I'll start off with the project background. So for the last 2 years, the Housner Fellows, we've been working on developing a data collection tool. It's essentially a survey. We noticed that most of the post-earthquake reconnaissance surveys mostly focus on damage, specifically structural damage. So we have been developing this tool to collect data on functional recovery, specifically functional recovery of buildings. And this tool we developed follows the 4 stages of functionality that are outlined in ATC 138. So we are hoping the data is something that can be used to validate these prediction methodologies that have been developed by others, but also inform functional recovery categories for different types of building uses and occupancies. Brief overview of some of the sections in our tool, as I will refer to some of these sections and the sample buildings later on. The 4 main groups of functionality checks that we collected data on are related to reoccupancy, tenant functions, architectural components, and external factors and impeding factors. The reoccupancy is something you would typically fill out as you're doing an ATC 20, for example, here in the United States, just focused on the structural damage. The tenant functions are components like the electrical, plumbing, HVAC, and elevators that are a little bit beyond the structural damage that we usually collect. So that's the second section. The third section focuses on the architectural components, finishes, whether exterior or interior, partition walls, ceilings, contents, and shelvings, and etc. And the big part is the external factors and the impeding factors. So we also collect data with our tool on external factors like failures to the power grid and how they affected the building's recovery, main water systems, main sewer systems, but also impeding factors such as financing of repairs and retrofits, permitting of repairs and retrofits, and material and labor shortage, and how all of those play into the delay, the overall delay in functional recovery of a building. So we had our tool almost at a draft level when the Hualien earthquake occurred in April, and we were able to travel to Taiwan almost 2 months after the earthquake. We were there from end of May to beginning of June for about 10 days. And we had integrated our survey into the EERI Fulcrum app that EERI uses for earthquake reconnaissance work. So these 3 screenshots are essentially the geotags of the buildings we collected data on. The one you see in the middle of the ocean is when we were playing around with the app on the train from Taipei to Hualien. But most of our data is located and concentrated in Hualien. We had one building we looked at in Taipei City. And the 2 photos on the right are close-ups of the proximity of the buildings we looked at. And most of the data we collected is obviously concentrated obviously on parts of the city that sustained the most damage. I'll go now into like some buildings that we collected data on and how the data we collected varied depending on the behavior of the buildings. So the first building, it's a 6-story steel moment frame building. It had concrete infill walls. A typical construction in Taiwan is to infill steel moment frames with concrete walls, or even sometimes to encase steel columns with concrete. So slightly stiffer behavior than the buildings that you would find in the US. This was a library building located in Donghua University in Hualien, and this building was partially functional. That was one of the questions in our tool, is how functional is a building? And the factors that played into its level of functionality were mostly related to non-structural damage. We observed a lot of bookshelves that had collapsed in the top 2 floors of the library. And also limited to those 2 top floors, we also saw a lot of ceiling tiles that have collapsed, as well as MEP distribution systems, like mostly ducts, that have collapsed on the top 2 floors. The structural damage, it was very minimal. The only structural damage that was observed at this building was limited to the concrete tower of the building. The building is 6 stories tall, like I mentioned, but there is a narrow and slender tower that extends beyond the roof of the building to about an additional 4 or 5 stories. And at that connection between the low roof of the building and the rest of the tower, at the base of the tower, there was a lot of concrete damage, concrete cracks and spalling, and some rebar exposed. So that was the only structural damage that was observed in the building. The steel moment frame connections, the beam to column connections, where we were able to see them. We didn't observe any damage in the fireproofing. And the reason we also labeled this building as partially functional is below the top 2 floors. The rest of the floors, like you can see in the photo on the right, did not have any damage. So when we first initially walked into the building, we didn't know the top 2 floors were still not functional. And there were no disruptions to the water, sewer, electrical systems to the building. The damage that was concentrated on the top 2 floors just disrupted the MEP system on the top 2 floors. There was one air handling unit on the top 2 floors that had slid off of its isolator. But outside of that, there was no system disruption. The second building I'll cover, it's also located at the same university. This is the administration building, and it's also a steel framed building with encased in concrete. This building was also partially functional. The damages similarly were concentrated on the upper 2 floors of the building. The non-structural damages we observed included ceilings and ducts that have collapsed. You will notice that this photo is a little bit more cleaner than the photo I shared with the library. The damage in this space has already been cleaned up when we went to do our reconnaissance work, and in some areas the repair had also started. The repair here, one of the factors that led into its delay was also availability of ceiling tiles. There was a shortage of ceiling tiles in the area at the time of our visit. So the library upper floor ceilings were not repaired. We also observed some structural damage in the administration building. On the top floor of the building, there was one stair where the stair stringer detached from the supporting beam at the mid-height landing. So it resulted in a partial collapse within the stair where one of the flights just had collapsed. And we also found a buckled steel brace. The brace connections are slightly different from the brace connections you would find in the US. The brace buckling and compression, we did not notice any failures within the connection. It was just the brace buckling and compression. And for this building, we also did not observe any disruptions to the water, the sewer, or the electrical system. Before I move into the third building, one thing I would like to note about the first 2 buildings, the 2 buildings had received both of the 2 buildings had received a yellow tag. So all of the lower floors were occupiable and accessible, and the top 2 floors that were not functional were barricaded off. The third building I'll go over, it's a concrete building with concrete infill walls. This would be a building you would consider as a non-ductile concrete building here in the US. It was about a 7-story tall residential building, and it was red tagged. So at the time of our visit, all the residents had evacuated, and we were able to gain access to some of the damaged areas of the building. This building is not functional, meaning people have not reoccupied it since the earthquake. The structural damage, the main structural damage that led to the red tagging of the building was the amount of cracks that were observed in one of the concrete beams on the ground floor. Just because of the location of the damage and how what could happen to that beam was critical to the rest of the building had received a red tag. As you can see from the photos, the building has also sustained a lot of non-structural damage. Most of the infill walls, almost all of the exterior infill walls were lightly reinforced concrete walls. about 6 to 8 inches walls with number force at very largely spaced amounts, and most of the partition walls, especially the demising walls between the apartments, were also concrete walls with, again, light reinforcing. So you see a lot of diagonal cracks, X formations in these walls, both on the exterior and the interior throughout the building. And whatever finishing was attached to these walls as a result had also fallen off. Last note about this building, there were no disruptions to the water, sewer, or electrical system outside of the structural components. All other systems of the buildings were still functional. They were turned off at the time of our visit because they were just getting, they were starting to mobilize to do the retrofit work for this building. The fourth building I'll go over, it's actually a brand new building. I don't even know if it's a brand new hotel. I don't know if it was open maybe for a couple of months before the earthquake. It's a steel moment frame building, and it has concrete infill walls in between the steel columns within the moment frames. We did not have access to the interior of this building. We only walked around the perimeter of the building. Most of the damage we observed were non-structural damage to the exterior wall. We saw a lot of plaster that had spilled off of the concrete walls. It was still restrained from falling by the netting that is part of the exterior facade of the building, but you can tell from walking on the streets on some floors that plaster spalling had occurred. We did also observe, some horizontal cracks in those concrete infill walls from the street level. Most of them were concentrated on the lower floors. And like I mentioned, we didn't have access to the interior of this building. And the last building I'll go over is another concrete building. This is again what we would consider as a non-ductile concrete building based on the lateral force resisting element as well as the age of the building. But this building had been retrofitted. This is a residential building. Original construction had a lot of open bays on the ground floor. The ground floor is used for parking, so there were no exterior and very minimal interior walls on that floor. So this building is what we would consider as a weak story building. And the retrofit included addition of new infill concrete walls only on the ground floor of the building. After the earthquake, at the time of our visit, this building was fully functional. The only damage we observed, as you can see from the photo on the right, is just very minimal minor cracks in some of the partition walls on the ground floor. And there were no disruptions to the water system, the sewer system, or the electrical system to the overall building. I believe there might have been a minor water main line break on the exterior of this building that they repaired by shutting down the water to the rest of the building, but they were able to do that within a few hours of the earthquake. So overall, the systems of the building and the functionality of the building were not greatly affected by the earthquake. Next steps for our project, we are updating our tool based on our findings from Taiwan. Collecting the data in Taiwan really gave us insight into what parts of our tool needed to be slightly adjusted, but also what additional context that we need to take into consideration in trying to collect data after an earthquake for functional recovery. And we're planning to publish our tool for the public use very soon, either as a paper or as a presentation somewhere. And I would like to conclude my presentation by saying thank you to ENCRI. They were of great assistance to us, to myself, Rahma, Wayne, and Leo, who travel to Taiwan. They made arrangements for us to look at all of these buildings that I discussed and more. And also the Hualien County government, they also gave us a lot of presentations and answered a lot of our questions on the impacts of the earthquake, specifically on some lifelines. Thank you very much.
Thank you very much, Maria. That was very nice presentation. I want to remind everyone that if you have some questions, you can go ahead and type them in the Q&A tab at the bottom of your screen. I see that we already have some questions, so I will go ahead and read some of those. The first one is for Dr. Li, and it asks if you could compare some of the nature of the ground motions in this earthquake to those from 25 years ago in the Chichi earthquake.
Yes, I think this time the type of ground motion is a little bit different. 25 years ago for Chichi earthquake is about fault movement, so we can observe about surface rupture. So especially it adverse force, so it impact a lot of buildings, especially not good quality building. But for the 2024, because the epicenter close to mountainous area, by its shaking, its intensities and the peak ground uncertainty is still very high. But the major difference, as mentioned by ENCRI, about is the frequency content. So anyhow, the magnitude and the duration for the Hualien earthquake is smaller, a little bit smaller than the Chichi earthquake 25 years ago. But however, as I mentioned, because we improved the building core, we also do some seismic retrofit to school. So compared to 25 years ago, the earthquake caused more than 300 school building collapse. But this one only caused one severe damage, but no collapse. So it showed though the ground motion about the same, but the results are different. Thank you.
Thank you. There's a question also if there was any damage to the Taiwan high-speed rail system in the west and north of Taiwan.
According to regulation of the high-speed rail, they will stop to check. But for this earthquake, actually, no direct damage to high-speed rail, even hours after the high-speed rail resumed its service. So no direct impact to high-speed rail. Actually, all the ground transportation along the west corridor, no impact.
You briefly show some damage to roads and tunnels, but there's a question on if you could expand a little bit on the damage to roads in general and in the Toroko National Park.
To Toroko National Park, there are two highways. One is highway number 9 from north to south. Another one is highway number 8 from east to the west. On highway number 1, north to south, a lot of falling rocks, especially from the Heren to Chongde section. A lot of falling rock interrupt the highway because huge rock falling on the rail, so it stopped the rail traffic. And a lot of rock slide on highway number 8 is the one that go through the Toroko National Park. But the 2 highway resumed its service 24 hours later because a lot of residents stay inside the Toroko Gorge. So it's very important to resume its service. But though it has a severe falling rock, but we can still maintain the minima operation after earthquake. So after earthquake, the impact to the highway is not so severe, though a lot of falling rock. But in the following, the Typhoon Kemi really brought severe damage to highway and railway because a cascading impact of the rock slide and mud slide caused the service interrupt to the highway, like 4 days, to the railway over a week. So to us, typhoon just create a source, but the torrential rain and typhoon bring the source down to the highway and railway.
Thank you. There's a question about power outages. You mentioned something about not having power outages, but is it really that there were absolutely no, or there were just a few minor ones?
I think just a few minor ones is unavoidable, but compared to 25 years ago, it's large-scale blackout. Especially at that time, it also caused the Hsinchu Science Park a severe damage because out of electricity. As I mentioned, in 1999, we only had one circuit around the Taiwan. So any point have kind of major failure, it might cause widespread breakout. But since then, we add more loops. So right now, if one loop have some power, of course, some area might have the minor power outage. But compared to the 25 years ago, our power grid now is more resilient than Chichi earthquake.
On a related question I had was, you talked about the CCTV video that worked very good and allow you to provide immediate idea of what was the states of streets and so on. And I was wondering if that it's sort of capable of working based on batteries and not rely on the grid.
Actually, because along the highway or in the city, most of the CCTV still rely on electricity, not the UPS, because it's widespread in the city. So we not just monitor one CCTV in Hualien City. We monitor several, maybe over a dozen in Hualien City. So we just pick up the one we can witness the collapse building. So in general, this time in Hualien, no large-scale impact because electricity. Of course, close to the collapse building for a safety reason, the Thai power company could shut down the power. So this is why we think most of the situation in Hualien City is stable. But in Toroko Gorge area, they suffer some power outage because there's some power line cut down by the falling rocks. So this is about the situation.
Thank you. There's a question regarding the early warning system that you briefly describe and being very successful and evolving since the late 90s. And the question is related, it's more effective at more distant sites, basically because you have a larger lead time. But in this case, it was very close to Hualien City. So how effective it was in this earthquake?
From the video in one driver's car, at that time, he was driving in the Toroko Gorge Park. The driver heard big sound from cell phone about earthquake. 2 seconds later, the falling rock hit the tunnel, and the driver kept safe because he was driving in the tunnel. So from this case, even in Hualien, Toroko Gorge, very close to the epicenter, they still have the few seconds. But we estimate even to Taipei City, we might have like the 10 seconds. So this is why our public education is always follow a shake idea, drop, cover, and hold on. That's a conceptual idea. You should think about how to do and what to do in case you heard the PWS on your cell phone. So in general, we think the PWS still function well this time. Besides, some estimation error about intensity in Taipei City, New Taipei City, and Taoyuan City. So the CWA didn't issue the warning to the 3 cities. But in general, all the other districts in Taiwan received the warning because this time is a countrywide earthquake early warning.
Okay. There's a question regarding the design standards for lifelines as opposed to other systems. And the question is if they're designed for the same standard levels for high seismic regions, lifelines such as power lines, water distribution systems.
Yes, we had a series of the improved design core or retrofit work, especially we defined those utility as the critical infrastructure. So in the last 25 years, decide increase or retrofit those facilities. Every few years, we also have the check about its preparedness, its contingency plan. So it is a continuous process to check our resilience in the critical infrastructure. So even about hospital, fire station, or power or a police station, sorry, we have to double check its resilience after we learn something from future earthquakes.
Thank you. I have a question for Maria. You know, one of the main things that you were looking for was to test this tool. And I was wondering if you found some areas of opportunity for further improvement of the tool, also, or as it was implemented, work well, and you don't think you need immediate sort of modifications to it.
There are two main areas that we learned can definitely use some improvement. One was just more of like an organizational feedback. We found it to be very easy to just talk to a building occupant or a building engineer and just make it more organic versus trying to say ask questions about, did your transformer go down? Did your generator go down? We found it to be more organic to just talk to them about, hey, what happened to your water distribution system? And they will just say, this part happened to that, this part happened. So we reorganized the order of some of our questions based on that finding. The second finding was, and we're going to write about this when we publish our tool, the financing part. The financing structure specifically in Taiwan is very different from the financing structure that I'm aware of would be the case after an earthquake here in the United States. The county government would provide a lot of assistance for building owners to help rebuild, retrofit their buildings. So that type of financing structure and the timeline associated with the availability of those financial resources would not be the same in every country. So our tool needs to take into account some level of context needed when you're collecting data on availability of financial assistance after an earthquake in various parts of the country. Those were the two main findings that we took with us to make adjustments to our tool.
On a related question, you know, I see a big difference, say, as you mentioned, ATC 20, which is mainly geared to the post-earthquake stability of a building and tries to capture it, you know, in an instant of time. And but now you have a much broader scope in terms of systems, non-structural systems, and even systems outside of the facility. But I was wondering how effective it was also to capture part of the evolution. One of the things that we're very interested in functional recovery is how fast and the different times in which different systems are coming back online, or they're partially recovered or fully recovered. And to what extent you think that worked in your tool?
We tried to kind of find a medium balance. The goal of functional recovery is like the basic intended function of a building. So we're not looking for full operational level of performance. So if there were, for example, some inconveniences that occupants had to withstand for a few days, but they didn't abandon the building and leave, that would be something we would note in our tool that we would be hard to note in an ATC 20 form. If there were some areas where owners just cleaned up the minor damage and just continued using the building, that type of data gathering would be hard to get with the current level of tools. So we tried to ask those questions and start those conversations, try to get to those points.
Okay. We have another question for Dr. Li, and it's related to mandatory seismic upgrade. You mentioned some of this happening in the schools, but is there, besides schools, other situations in which there's a mandatory upgrade for structures? or buildings?
Except the schools mandatory retrofit to hospital, no matter public or private hospital, they must receive the retrofit program assigned by government. Otherwise, they cannot receive some subsidy due to our health insurance system. Other things like fire or police station, there are several must receive voluntary retrofit. But our issue still on the private buildings, because most of residents, they hesitate in applying kind of government fund to do evaluation on their houses, or afterward they have paid money to retrofit the house. So something worries us a lot is about the old existing building. Those buildings lower than 5-story only have one escape later stairs. Those are kind of the very vulnerable building, especially in Taipei City, over 100,000 buildings like this. So this is why we want to have like urban renewal or other policy to motivate people try to accept a kind of retrofit is a must be. So we have to make progress, but we still have some challenge till now. Thank you.
Thank you. There's a question for Maria. If you have plans to go back to Taiwan to sort of follow up on some of these buildings and try to capture how they have continued to recover, or if you don't have plans, if you have some sort of way of through colleagues at EERI that they would do that follow-up.
I'm pretty sure I've promised that I would probably go back to Taiwan if I could. It would be great for us to do that. Currently, we don't have any plans to do a return trip in the near future, but that's something definitely we would love to do. We are definitely staying in touch with some of our colleagues from EERI who were very instrumental to our work when we were there, and like tracking the recovery and some of the standards that will be used for the repairs is the follow-up conversations we've been having with them.
Perfect. So thank you very much for both of our speakers. I think we went through all of the questions that were typed. I want to reiterate and remind everyone about that survey that we have at the end, and to also let you know that the this webinar, in addition to the one that we had 2 weeks ago, will be available shortly on our website. So if you know of someone that was not able to watch it today, but may be interested in this, please let them know that it's going to be available on our website.
Great. Thank you so much to Eduardo for moderating, and to both of our speakers for taking the time to join us, and to the audience as well. Just a note, a survey will pop up in the screen after this closes, and you'll get it by email. That's actually a survey for the webinar, but I've put a link into it to the survey on LFE interest for reconnaissance agendas and future projects. So we'd very much appreciate it if you could take the time to share your input on both. Just a reminder that you can learn about EERI and how to join at our website. You can find out about upcoming webinars there as well, and also about LFE's work in the LFE endowment. And then finally, I just want to note that this webinar series, as noted, is supported by the LFE endowment, by cooperative agreement with FEMA, and also by EERI members like yourself. So thank you for making this work possible. And we'll have these recordings